Okay, let's discuss some properties of functions. Continuity is one. You can see here graphed a function. This is probably a polynomial. Polynomials are continuous everywhere. Continuous means that it doesn't have any holes, it doesn't have any breaks. It is exactly what it sounds like. It just continues forever in both directions, and there's nothing to interrupt it. Alright, so sometimes you might have just a plain hole in your graph, okay? A place in the domain where there is no function. Okay, so the domain means what can x equal? Well, in this graph, x cannot equal a, which looks to be about maybe -2 or something like that. Sometimes you have a random jump, where your function will be going along and all of a sudden, instead of having a point where there should be, there's a point somewhere else. Okay, so in this case, this is also discontinuous because it's not that x cannot be a, it's just that when x is a, y is something weird. Okay, so there's a little jump. So that's one example of discontinuity. There's another example where a function will be going along and all of a sudden the whole function will jump and keep going from there. Okay, so that's another discontinuity. Or you could have a function that has maybe an asymptote, goes down, okay, keeps going down, never actually touches a, and then it comes from the top and keeps going, but it skips over a. So in this case, a is not even in the domain. So those are just some various examples of discontinuity. Okay, we can look at a graph to see if it's continuous everywhere, but if you have a function that is a polynomial, so a polynomial would be something like y equals 2x squared plus 3. Okay, notice that there's no square roots in this, there's no x's in the denominator, there's no weird things going on in this function. Okay, so in functions like this that are polynomials, so another example would be y equals 4x to the 17th plus 2x to the 5th, okay, plus 9x maybe. Okay, so anything that looks like a polynomial is going to be continuous everywhere. Okay, polynomials are continuous. But when you start running into problems, that's when you have maybe like, let's say 10x to the -2. Okay, negative exponent. That negative exponent means that this x is really in the denominator. So remember that this is the same thing as 10 over x squared. And so when you have an x in the denominator like this, that's when you start running into some discontinuity. Alright, so just be careful about that. Okay, what else do we have here? Let's look at increasing and decreasing. So functions can go up, they can go down, or they can remain constant. So this function, as we go from left to right, is going up. So that would be called increasing. This function, as we go from left to right, is going down. So that's decreasing. And constant is when we have a straight line that slope is 0. So just remember, in this case, we have the slope of this line is 0, right? A vertical line has undefined slope, but a horizontal line has 0 slope. All right. Sometimes functions can have all three, increasing, decreasing, and constant, in the same graph. Okay, so this function is decreasing from -infinity all the way up to -2. Okay, notice how they write that, from -infinity to -2, including -2. This is the interval notation for where this function is decreasing. And then the function is constant in the middle, from -2 to 2. Okay, so again with the brackets, -2 to 2, it's constant, it's flat. And then it's increasing from 2 on. Okay, so they write that bracket 2 and then infinity parentheses. Okay, so it's increasing. So it can happen all in the same function, and you can have various forms of that as well. Okay, let's see what else we have. Sometimes you might have to tell if something is increasing, decreasing, or constant just based on a table. So let's look at this. Notice that x is going up in this table. What is happening to y? Okay, it's exactly the same. So this would be an example of a constant function. Okay, constant. Okay, in this case, x is increasing and the y's are getting smaller. Okay, so this would be an example of a decreasing function. Okay, x is increasing, y is decreasing. Okay, and in this one, x is increasing again, and y is also increasing. They're going up together. So if they're going up together, if they're the same, then it's increasing. All right, great. Okay, boundedness. To say a function is bounded means that there's something that it can't be going up or something that it can't be going down. It's talking about a range, having a maximum or a minimum. So let's look at this one as an example. This function right here, it has a lowest point. Okay, notice that it never gets lower than this line right here. Okay, it goes up for forever, but it doesn't go further down than this. So we would say it's bounded below. Okay, it's not bounded above, it keeps going, but it is bounded below. This one right here has a topmost point, a maximum. Okay, it doesn't go higher than this point right here. It does go down, so we say it's bounded above, okay, but it doesn't go down. And then this one, this random squiggle, it has top points and it has bottom points. Okay, so it is, we just say bounded. That means it's bounded above and below. It doesn't go any further up or down. Whereas this one, the first one over here, it keeps going up forever and it keeps going down forever. So it's just, we say it's not bounded. It's not bounded above or below. It's just not bounded. Okay, and so another good example of something that maybe is bounded, just entirely bounded, would be something like a sine function. I don't know if you've graphed y equals, so you can go to your calculator, graph y equals sine of x. Okay, type that into y1 and graph it and see what it looks like. But it looks like this. I'll just go ahead and do a quick graph for you, and it keeps going in this pattern like this. Okay, so it's a squiggle that just keeps going and going and going, and it is bounded above and below. The topmost point is 1, the bottommost point is -1. Let's see. Okay, we talked about bounded below and a lower bound. The lower bound is the point that is the lowest point. So for example, in this problem right here, we have this lowest point down here is -4. So we would say -4 is a lower bound for this graph. Okay, and it works the same way with an upper bound. All right. Let's talk about extrema. Okay, local and absolute extrema. All right, so here's a good example. This is a function that is bounded below, and it has this minimum. This is its lower bound, okay? You can see that the minimum looks to be about -24, okay? But it also has this little bitty minimum over here. It's not an absolute minimum. Absolute minimum means this is the minimum for the entire graph. This is the lowest the entire graph will ever go, okay? But a local minimum right here is a minimum on a certain domain. So you can restrict the domain and come up with a lowest point. So it's called a local minimum because in this area over here, this is the lowest point in the area. Okay. If we extend the domain past that, if we say right here, what's the lowest point in this area? Well, this would be the local minimum on this domain. Okay, so just be careful about that. How are you restricting the domain? okay, because this would be the lowest point if we consider this domain right here. Okay, but if we stick with this area right here, then this is the lowest point. This is the local minimum. And again, this point right here is the absolute minimum. It's the minimum for the entire graph. No matter where we restrict the domain, this is still the lowest point of the whole graph. All right. And it works the same, of course, for maximum, local maximum, local and absolute maximum. Okay. Symmetry. I think we talked about this before in Algebra 2. If you have a function that is symmetric on the y-axis, what does it mean to be symmetric? That means it's a mirror. So if you take this side, you can flip it over to this side. Okay, flip it over like a mirror, and you would have the exact same thing. So if it's symmetric on the y-axis, okay, on this axis right here, you could just flip this over. Then we say that the function is even. Okay. Even means you can flip it over on the y-axis. And if you don't have a graph and you're not sure, is it an even function? I don't know. Then what you do is this property, okay? And let me go ahead and do an example of that for you. So let's go to a different page. Okay. Let's say we have the function y equals x to the fourth. Okay, we want to know, is it even? Well, hint, it is even because the highest power is 4. Okay, 4 is an even number, so it's going to be an even function. But let's test to make sure. Remember, the rule says f of x, sorry, not f of x, f of negative x has to equal f of x. That's how we tell if it's an even function. So what we do is we'll go ahead and plug in negative x. Sorry. Let's plug in y equals, if we plug in negative x into our function, okay, what do we get out? What happens if you multiply negative x times negative x times negative x 4 times? Okay, well, all the negatives are going to cancel out because it's an even number of negatives. So we have x times x times x times x. Okay, 4 x's. So that would be x to the fourth. Now, does this equal the original? Yes, it sure does. It sure does. So that would be an even function because it works out like that. Okay, great. Let's go back. Let's look at maybe an odd function. So if it's an odd function is one that is symmetric around the origin. So this is the origin right here. This means that if you take this graph and swing it around 180 degrees, it will be the same. That's what it means to be symmetric around the origin. So if we swing this graph around 180 degrees, do we have the same thing that we started with? Okay, and so notice that this is an odd function, and notice the rule for this one. Okay, the other rule for even was, for even functions, we had f of negative x equals what we started with, f of x. But in this case, we have f of negative x equals negative f of x. So it's a little bit different. It has this extra negative in front, and that's for odd functions. Okay? Well, let me show you an example of how that might work if you don't have a graph. Okay, so we would have, let's start with y equals, let's say x cubed. Okay, this is an odd function. So it is an odd function. It has an odd power of x, so that's just a little hint. 3 is odd, so it's going to be an odd function. But let's go ahead and check it algebraically just to make sure. We want to know, is f of negative x the same thing as negative f of x? Okay, so let's plug in negative x. So y equals negative x cubed. Okay. What would this be? This would be negative x times negative x times negative x. So what's our answer going to be? Well, 2 of the negatives will cancel out, but we'll still have 1, right? So negative, and then we have x times x times x. So that is negative x cubed. Now, the question is this the same thing as negative f of x? So what does this mean? This means take the original, which was y equals x cubed, and stick a negative in front. So stick a negative in front, and then we want to know, are they the same? Are these two things the same? And they are. Okay, so this is an odd function. All right, great. Okay, let's see if we have anything else. Okay, asymptotes we're going to go over in the next video.